Hey everyone, so this is the second video on linear motion where we're now going to talk about scalars and vectors. We talked about before how we have these two different types of measurements that both tell you how far you've traveled, but they give slightly different pieces of information. In particular, they handle differently in the sense that one of them doesn't really care about direction while the other one does and will change accordingly. Uh, Going in one direction is different than going in a different direction. And that's related to this. Now, both of these are actually more math terms, but we can still use it in this class. So, what we're going to find out is that every measurement that we have in this class can be put into one of these two categories. If it's put into the scalar category, then that means that it's a measurement that only gives us a magnitude, or another way of saying that is its size. Good examples of this would be your height, your age, distance, as we saw before. All of these are things that you wouldn't ever really add a direction to. Telling someone that you're 6 feet tall north doesn't really mean anything. Time is another perfect example of something where, adding a direction to it doesn't really make much sense. It's a measurement that only has a value, and in many cases, really only ever goes up. Vectors, on the other hand, they're measurements that have both magnitudes and direction. So again, these are examples. So telling someone not only how far away you are, but the direction is a vector. The telling someone how fast you're going in a certain direction is another vector. Um, Telling someone that you got pushed to the right is kind of a vector. It doesn't really have a magnitude, but it still has that same idea that that action is a vector as opposed to a scalar. In the regions class, we have a regions and AP class. There's a very common set of scalars and vectors that you need to be aware of. Now, throughout the course, we're going to constantly be referring back to it, saying which ones are scalars, which ones are vectors. But it's good to kind of have everything written down. So this is a list of the scalars, and over here are the vectors. For the most part, even though it looks like there's an equal amount, there's actually significantly more scalars than there are vectors. In particular, there really is only about five, maybe six vectors that are covered by both, well, by the regions especially. AP probably has another, three or four vectors in there. But compared to the scalars, it's almost infinite. Essentially, if you see something that's not on this list, chances are it's a scalar. One thing you may notice though is that I have two measurements colored purple and two colored blue. That's because these two are usually referred to as scalar vector pairs, in the sense that they're both measurements of the same thing, but one's a scalar, the other one's a vector. So, for example, if we are finding how far someone travels, the scalar version of how far someone travels is distance. The vector version is displacement. Same thing with speed and velocity. The main point of this is that something like mass or acceleration or time or force don't really have an alternate version. There's no vector version of time or a scalar version of mass. So sometimes it's important to remember that those two or four are kind of linked. If you've ever seen the movie Despicable Me, one thing you should note about this character is that his name is Victor, but he loves to go by the name Vector. And he claims that the reason he goes by the name Vector is because his crimes carry both magnitude and direction. All right, so there's a bunch of different properties that you need to be aware of about vectors. They get brought up so much that it really is useful knowing right off the bat how they work. So, like I said, vectors have both this magnitude and direction, but one of the nice thing about vectors is that you can kind of draw out pictures and use the vector notation and these properties to actually represent the measurements. Typically, vectors are usually represented by an arrow, and the arrow will have different things like a length that represents its magnitude, and a direction that obviously represents the direction it's going in. So if I draw two vectors, if I draw two vectors, call this A and vector B, you can immediately tell the difference between A and B. You could tell me which one's bigger, which one's smaller. If I draw vectors like this, you can tell me pretty much where you're supposed to be. So there's a lot of things that you can get, a lot of information you can get from images of these vector diagrams. One thing to note is that if you take a vector and you multiply it by a positive scalar, the only thing that really changes is the value, the size, the magnitude. So doing 1 meter to the right, timesing that by 3, gives us 3 meters to the right. If I instead did times by 0.3, then it would be 0.3 meters to the right, so it would get a little bit smaller. But essentially, the value, the length of the arrow changes, the value that it represents changes. On the flip side, if we multiplied it by a negative scalar, what we end up getting is that not only does the magnitude change, but the direction also flips directions. Now, this carries very important meaning in the sense that when we talk about vectors and we start giving them numerical values, a lot of times you're going to start seeing positive and negative vectors. The negative in the vector, when it comes to vector notation, is usually used to represent a different direction. So if you're doing a problem and they're not really specifying a specific direction, but they say that you're going in some general direction, but then during your calculations, something's pointed in the other direction, you need to make sure that you make that vector negative, because that's what negative means when it comes to vectors. It means other direction. If you're moving to the right and something's pushing you to the left, then the vector that's representing that push to the left has to be represented as a negative vector. We can take multiple vectors. Kind of already saw this in some of the other questions, but we can take multiple vectors and combine them together into what we call a resultant vector. There's two different ways that we could do this. Each one carries with it a positive and negative, a strength and a weakness. One method that you could use is what we call a graphical method, or what I like to call a tip-to-tail method. And basically what this is that you draw out the diagram in such a way that the arrows point, so that you draw an arrow, and then from the end of one arrow you draw the next arrow, and then the next and the next, and you have to make sure that you draw the arrows to scale. If you do that, you can then draw a line going from where that path starts to where it ends, and you can get your resultant. In fact, if you go back to the previous one of the previous slides where I had an image of the distance and displacement that looked something like this, and then I said that the displacement went from here to here, from start to finish, this could actually be considered as this type of setup, where this represents all these tiny little vectors pointing in the direction that you've traveled. And then down here, the final arrow that goes from start to finish, this dotted line that we would call the final displacement, is actually a resultant vector. So we've already done a few of these in class and in some of the videos, but we're going to go into a little bit more detail and spread it out to not just displacements and distances, but to all vectors. Now, the one thing is that in order to do this, first, like I said, you have to draw these vectors to scale. So you have to make sure that they have appropriate lengths relative to their sizes. But so you also are going to need a ruler for this. But you're essentially going to have to make sure that you draw it like a treasure map. So again, you have an arrow drawing one way, then from there it gets to the next, and then from there you go to the next, and to the next, and so on and so on. You shouldn't have arrows pointed towards each other, or arrows going off in different directions like this. So this is not a tip-to-tail method. Now, One thing I wanted to point out is I'm going to start off with the simpler cases. Obviously, with the simple cases, you would not be using this method unless explicitly asked. Typically, this method is going to be used more for setups where the diagrams are very complicated, where you have a ton of vectors in completely different directions. There's a bunch of weird angles, all this crazy stuff. That's the type of scenario where doing it graphically actually ends up being the easier thing. But one thing you'll notice is that in a few of these questions, you might think, oh, there's a better way. And of course, there's always a better way. So I just want to point that out. So here, let's say we're doing the scenario where I travel 5 meters east, 10 meters west, and then 3 meters east. And I want to know, what is my final displacement? Essentially, I have 3 displacement vectors, 5 meters east, 10 meters west, and 3 meters east, and I'm looking for my resultant displacement. First thing that you have to do when you do tip to tail is you have to come up with a proper scale. So you have to figure out, 1 centimeter represents how many meters. One example you could do is 1 centimeter equals 1 meter. If the values are too big and that doesn't fit on your paper, you can go somewhere up to 1 centimeter equals 2 meters, 1 centimeter equals 5, something like that. But you always have to figure out what scale works, and you have to notate it somewhere in your diagram so someone can actually do that conversion and trace out what you're doing. Then, starting at some point, either a point that's given to you or a point wherever you want, you start drawing the vectors to scale. So the first vector of 5 meters east, I would draw a 5 centimeter line going to the right, 10 centimeter line going to the left, and then 3 centimeter line going to the right again. Another thing to note is when you draw these vectors and you're doing these vector diagrams, you need to make sure that you have arrowheads indicating their proper direction and also the value that these arrows are representing. You should not have written 5 centimeters. Like, you're not telling me how long the line is in reality. I want to know, what is that top line supposed to represent. From here, that's our vector diagram. Now what we can do is we could draw a line going from the starting point, which is right here, to the ending point, and that will end up being our resultant. So we draw an arrow going to the final, not making a full loop. We go to the final location. Again, making sure to put that proper arrowhead. And then what we would do is, depending on our scale, we would measure this line and then figure out what the value is. So again, in this case, we had a 1 centimeter to equals 1 meter conversion. So a 2 centimeter line would give me 2 meters. So in the end, my displacement would end up being 2 meters west. Here's an example where you might want to use tip to tail. This also isn't really a perfect example of when you would use 2D, but you can kind of see how maybe doing it mathematically may not be the easiest case, or at least maybe not right off the bat. But we could do, like I said, draw out the paths, and then again we go from start to finish, draw a line, and then we can measure this to figure out what the magnitude of that resultant is. The one thing to note is that when you have your resultant going off at an angle like this, one thing you might have to do is measure the angle from some horizontal line. So you can use a protractor, measure this angle to figure out what angle it is with respect to the x-axis. If you weren't drawing this out, then you'd have to mathematically figure out the angle, which again can be tricky depending on how the diagram is drawn. So here's some food for thought type questions. First, why would this method not be as accurate? So try to think about this. In addition, think about some of the other ones. Like, do you think we would get more accurate results if we use the bigger diagram or a smaller diagram? And then, does the order in which I draw the vectors matter? Now, for the first one, why would this method not be accurate? Well, there's a ton of reasons. First, people make mistakes when measuring rulers. Sometimes, especially if the arrow is fairly small on the ruler, it's very easy to misread, a millimeter or two here or there. So that's one reason. Another reason is sometimes people will measure a line and it might be pretty good, pretty perfect. But then the arrow that they draw is a little off centered. And then when they draw the next arrow from there, there's now this extra distance added in. Another thing is maybe you're supposed to draw a line that goes horizontal and vertical, and I'm doing this on a mouse, so it kind of explains why it's not perfect, but you might actually draw a line that is slightly on an angle. So all these little factors can affect the accuracy. In fact, typically the more arrows you add into the problem, the lower the accuracy ends up being. If you have 2 arrows versus 20 arrows, the 20 arrows is going to end up being not nearly as accurate. Now the next one is, would we get more results or more accurate results if we use bigger or smaller? It makes the most sense that we would use a bigger diagram. If we go back to our discussion about error, if let's say our largest arrow that we draw is about 5 centimeters long. For the most part, this is going to be 5 plus or minus 0.1 centimeters. For this could end up resulting in a fairly big error compared to a bigger diagram where maybe my biggest actually is 50 centimeters. And we still have that same error of plus or minus 0.1 centimeters. So here we could see that this error that comes naturally from the ruler won't play nearly as big of a part when my number is very big versus very small. And the smaller this is, the bigger this systematic error from the ruler plays a part. Now the third part is, does order matter? So does it matter whether or not I put which vector first versus second? And for this one, I have a really good simulator where I can show this. So over here I have a PhET simulator, and I can show whether or not order actually matters. So let me pull over 3 different vectors. Let me actually get rid of pen mode. Oh, I guess I didn't get rid of pen mode. And my resultant will go from the start to the finish, like that. Now, let's say I reorder this. Maybe instead of going A, B, C, I switch to C and the B. I land in the same spot. What if I move the C down here and then A over here? I can't do that, so I have to shift everything up a bit. And land in the same spot. Let's switch the C, the B, the C, and then the A. Gotta shift it up a bit. And there you go. So it doesn't matter what order I put it in. I can arrange this in every single possible order. I can add a 4th, a 5th, a 6th. I could go all the way up to an infinite number of vectors. As long as I maintain their magnitude and direction, they will always land in the same spot. What I mean by this is that you want to make sure that if you are going to redraw the vectors so that they're tip to tail, you need to make sure that the angles, if there are any vectors that are at angles, the angles are maintained, the location of the arrowheads maintained, the length of the vector is maintained, everything about it is the same. You're just dragging it over to a different spot. That's all you're doing when you're doing things like this. And when you think about it, it does kind of make sense. You're still taking the same paths. If you go right 100 meters and then you go you go east 100 meters and then north 100 meters, that's the same as going north 100 and then east. So as long as you do the same paths for the same values, it makes sense that you land in the same spot. All right. That's it for the graphing method. There is a second method where I'm going to talk a little bit about the math. Like I said, one of the benefits of the tip to tail method, or being able to draw it out graphically, is that it's very easy to get the resultant regardless of how complicated it is. As you could see here, if I was giving you these three vectors, it wouldn't be that easy to mathematically calculate this. Even when I show you how you can do it, you'll realize that for a scenario like this, drawing it out and then measuring the line is significantly easier than having to mathematically calculate each vector in order to figure out the resultant vector. All right, so just keep that in mind that there are benefits to the tip to tail method, even though a lot of the practices that we've done were the simple cases. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.